star of more than about 1.5 times the mass of the Sun would not be able to support itself against its own gravity. This mass is now known as the Chandrasekhar limit. This had serious implications for the ultimate fate of massive stars. If a star's mass is less than the Chandrasekhar limit, it can eventually stop contracting and settle down to a possible final state as a white dwarf, with a radius of a few thousand miles and a density of hundreds of tons per cubic inch. A white dwarf is supported by the exclusion principle repulsion between the electrons in its matter. We observe a large number of these white dwarf stars. One of the first to be discovered is the star that is orbiting around Sirius, the brightest star in the night sky. It was also realized that there was another possible final state for a star, also with a limiting mass of about 1 or 2 times the mass of the Sun, but much smaller than even the white dwarf. These stars would be supported by the exclusion principle repulsion between the neutrons and protons, rather than between electrons. They were therefore called neutron stars. They would have had a radius of only 10 miles or so, and a density of hundreds of millions of tons per cubic inch. At the time they were first predicted, there was no way that neutron stars could have been observed, and they were not detected until much later. Stars with masses above the Chandrasekhar limit, on the other hand, have a big problem when they come to the end of their fuel. In some cases they may explode or manage to throw off enough matter to reduce their mass below the limit. But it was difficult to believe that this always happened, no matter how big the star. How would it know that it had to lose weight? And even if every star managed to lose enough mass, what would happen if you added more mass to a white dwarf or neutron star to take it over the limit? Would it collapse to infinite density? Eddington was shocked by the implications of this, and refused to believe Chandrasekhar's result. He thought it was simply not possible that a star could collapse to a point. This was the view of most scientists. Einstein himself wrote a paper in which he claimed that stars would not shrink to 0 size. The hostility of other scientists, particularly of Eddington, his former teacher and the leading authority on the structure of stars, persuaded Chandrasekhar to abandon this line of work and turn instead to other problems in astronomy. However, when he was awarded the Nobel Prize in 1983, it was, at least in part, for his early work on the limiting mass of cold stars. Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. But the problem of understanding what would happen to such a star, according to general relativity, was not solved until 1939 by a young American, Robert Oppenheimer. His result, however, suggested that there would be no observational consequences that could be detected by the telescopes of the day. Then the war intervened, and Oppenheimer himself became closely involved in the atom bomb project. And after the war, the problem of gravitational collapse was largely forgotten, as most scientists were then interested in what happens on the scale of the atom and its nucleus. In the 1960s, however, interest in the large-scale problems of astronomy and cosmology was revived by a great increase in the number and range of astronomical observations brought about by the application of modern technology. Oppenheimer's work was then rediscovered and extended by a number of people. The picture that we now have from Oppenheimer's work is as follows. The gravitational field of the star changes the paths of light rays in space-time from what they would have been had the star not been present. The light cones, which indicate the paths followed in space and time by flashes of light emitted from their tips, are bent slightly inward near the surface of the star. This can be seen in the bending of light from distant stars that is observed during an eclipse of the Sun. As the star contracts, the gravitational field at its surface gets stronger, and the light cones get bent inward more. This makes it more difficult for light from the star to escape, and the light appears dimmer and redder to an observer at a distance. Eventually, when the star has shrunk to a certain critical radius, the gravitational field at the surface becomes so strong that the light cones are bent inward so much that the light can no longer escape. According to the theory of relativity, nothing can travel faster than light. Thus, if light cannot escape, neither can anything else. Everything is dragged back by the gravitational field. So one has a set of events, a region of space-time from which it is not possible to escape to reach a distant observer. This region is what we now call a black hole. Its boundary is called the event horizon. It coincides with the paths of the light rays that just fail to escape from the black hole. In order to understand what you would see if you were watching a star collapse to form a black hole, one has to remember that in the theory of relativity there is no absolute time. Each observer has his own measure of time. The time for someone on a star will be different from that for someone at a distance, because of the gravitational field of the star. This effect has been measured in an experiment on Earth with clocks at the top and bottom of a water tower. Suppose an intrepid astronaut on the surface of the collapsing star sent a signal every second, according to his watch, to his spaceship orbiting about the star. At some time on his watch, say 11 o'clock, the star would shrink below the critical radius at which the gravitational field became so strong that the signals would no longer reach the spaceship. His companions watching from the spaceship would find the intervals between successive signals from the astronaut getting longer and longer as 11 o'clock approached. However, the effect would be very small before 10:59 and 59 seconds. They would have to wait only very slightly more than a second between the astronaut's 10:59 and 58 second signal and the one that he sent when his watch read 10:59 and 59 seconds, but they would have to wait forever for the 11 o'clock signal. The light waves emitted from the surface of the star between 10:59 and 59 seconds and 11 o'clock by the astronaut's watch would be spread out over an infinite period of time, as seen from the spaceship. The time interval between the arrival of successive waves at the spaceship would get longer and longer, and so the light from the star would appear redder and redder and fainter and fainter. Eventually, the star would be so dim that it could no longer be seen from the spaceship. All that would be left would be a black hole in space. The star would, however, continue to exert the same gravitational force on the spaceship. This is because the star is still visible to the spaceship, at least in principle. It is just that the light from the surface is so redshifted by the gravitational field of the star that it cannot be seen. However, the redshift does not affect the gravitational field of the star itself. Thus the spaceship would continue to orbit the black hole. The work that Roger Penrose and I did between 1965 and 1970 showed that, according to general relativity, there must be a singularity of infinite density within the black hole. This is rather like the Big Bang at the beginning of time, only it would be at the end of time for the collapsing body and the astronaut. At the singularity, the laws of science and our ability to predict the future would break down. However, any observer who remained outside the black hole would not be affected by this failure of predictability, because neither light nor any other signal can reach them from the singularity. This remarkable fact led Roger Penrose to propose the cosmic censorship hypothesis, which might be paraphrased as, God abhors a naked singularity. In other words, the singularities produced by gravitational collapse occur only in places like black holes, where they are decently hidden from outside view by an event horizon. Strictly, this is what is known as the weak cosmic censorship hypothesis. Protect observers who remain outside the black hole from the consequences of the breakdown of predictability that occurs at the singularity. But it does nothing at all for the poor unfortunate astronaut who falls into the hole. Shouldn't God protect his modesty as well? There are some solutions of the equations of general relativity in which it is possible for our astronaut to see a naked singularity. He may be able to avoid hitting the singularity and instead fall through a wormhole and come out in another region of the universe. This would offer great possibilities for travel in space and time, but unfortunately it seems that the solutions may all be highly unstable. The least disturbance, such as the presence of an astronaut, may change them so that the astronaut cannot see the singularity until he hits it and his time comes to an end. In other words, the singularity always lies in his future and never in his past. The strong version of the cosmic censorship hypothesis states that, in a realistic solution, the singularities always lie either entirely in the future, like the singularities of gravitational collapse, or entirely in the past, like the Big Bang. It is greatly to be hoped that some version of the censorship hypothesis holds, because close to naked singularities, it may be possible to travel into the past. While this would be fine for writers of science fiction, it would mean that no one's life would ever be safe. Someone might go into the past and kill your father or mother before you were conceived. In a gravitational collapse to form a black hole, the movements would be dammed by the emission of gravitational waves. One would therefore expect that it would not be too long before the black hole would settle down to a stationary state. It was generally supposed that this final stationary state would depend on the details of the body that had collapsed to form the black hole. The black hole might have any shape or size, and its shape might not even be fixed, but instead be pulsating. However, in 1967, the study of black holes was revolutionized by a paper written in Dublin by Werner Israel. Israel showed that any black hole that is not rotating must be perfectly round or spherical. Its size, moreover, would depend only on its mass. It could in fact be described by a particular solution of Einstein's equations that had been known since 1917, when it had been found by Karl Schwarzschild shortly after the discovery of general relativity. At first, Israel's result was interpreted by many people, including Israel himself, as evidence that black holes would form only from the collapse of bodies that were perfectly round or spherical. As no real body would be perfectly spherical, this meant that in general gravitational collapse would lead to naked singularities. There was, however, a different interpretation of Israel's result, which was advocated by Roger Penrose and John Wheeler in particular. This was that a black hole should behave like a ball of fluid. Although a body might start off in an unspherical state, as it collapsed to form a black hole, it would settle down to a spherical state, due to the emission of gravitational waves. Further calculations supported this view, and it came to be adopted generally. Israel's result had dealt only with a case of black holes forming from non-rotating bodies. On the analogy with a ball of fluid, one would expect that a black hole made by the collapse of a rotating body would not be perfectly round. It would have a bulge round the equator, caused by the effect of the rotation. We observe a small bulge like this in the Sun, caused by its rotation once every 25 days or so. In 1963, Roy Kerr, a New Zealander, had found a set of black hole solutions of the equations of general relativity more general than the Schwarzschild solutions. These Kerr black holes rotate at a constant rate, their size and shape depending only on their mass and rate of rotation. If the rotation was zero, the black hole was perfectly round, and the solution was identical to the Schwarzschild solution. But if the rotation was non-zero, the black hole bulged outward near its equator. It was therefore natural to conjecture that a rotating body collapsing to form a black hole would end up in a state described by the Kerr solution. In 1970, a colleague and fellow research student of mine, Brandon Carter, took the first step toward proving this conjecture. He showed that, provided a stationary rotating black hole had an axis of symmetry, like a spinning top, then its size and shape would depend only on its mass and rate of rotation. Then, in 1971, I proved that any stationary rotating black hole would indeed have such an axis of symmetry. Finally, in 1973, David Robinson at King's College London used Carter's and my results to show that the conjecture had been correct. Such a black hole had indeed to be the Kerr solution. So after gravitational collapse, a black hole must settle down into a state in which it could be rotating, but not pulsating. Moreover, its size and shape would depend only on its mass and rate of rotation, and not on the nature of the body that had collapsed to form it. This result became known by the maxim, "A black hole has no hair." It means that a very large amount of information about the body that has collapsed must be lost when a black hole is formed, because afterward all we can possibly measure about the body is its mass and rate of rotation. The significance of this will be seen in the next lecture. The no-hair theorem is also of great practical importance because it so greatly restricts the possible types of black holes. One can therefore make detailed models of objects that might contain black holes and compare the predictions of the models with observations. Black holes are one of only a fairly small number of cases in the history of science where a theory was developed in great detail as a mathematical model before there was any evidence from observations that it was correct. Indeed, this used to be the main argument of opponents of black holes. How could one believe in objects for which the only evidence was calculations based on the dubious theory of general relativity? In 1963, however, Martin Schmidt, an astronomer at the Mount Palomar Observatory in California, found a faint star-like object in the direction of the source of radio waves called 3C273, that is, source number 273 in the third Cambridge Catalogue of Radio Sources. When he measured the redshift of the object, he found it was too large to be caused by a gravitational field. If it had been a gravitational redshift, the object would have been so massive and so near to us that it would disturb the orbits of planets in the solar system. This suggested that the redshift was instead caused by the expansion of the universe, which in turn meant that the object was a very long way away. And to be visible at such a great distance, the object must be very bright and must be emitting a huge amount of energy. The only mechanism people could think of that would produce such large quantities of energy seemed to be the gravitational collapse, not just of a star, but of the whole central region of a galaxy. A number of other similar quasi-stellar objects, or quasars, have since been discovered, all with large red shifts. But they are all too far away and too difficult to observe to provide conclusive evidence of black holes. Further encouragement for the existence of black holes came in 1967 with the discovery by a research student at Cambridge, Jocelyn Bell, of some objects in the sky that were emitting regular pulses of radio waves. At first Jocelyn and her supervisor, Anthony Hewish, thought that they maybe had made contact with an alien civilization in the galaxy. Indeed, at the seminar at which they announced their discovery, I remember that they called the first 4 sources to be found LGM 1-4, LGM standing for Little Green Men. In the end, however, they and everyone else came to the less romantic conclusion that these objects, which were given the name pulsars, were in fact just rotating neutron stars. They were emitting pulses of radio waves because of a complicated indirection between their magnetic fields and surrounding matter. This was bad news for writers of space westerns, but very hopeful for the small number of us who believed in black holes at that time. It was the first positive evidence that neutron stars existed. A neutron star has a radius of about 10 miles, only a few times the critical radius at which a star becomes a black hole. If a star could collapse to such a small size, it was not unreasonable to expect that other stars could collapse to even smaller size and become black holes. How could we hope to detect a black hole, as by its very definition it does not emit any light? It might seem a bit like looking for a black cat in a coal cellar. Fortunately, there is a way, since, as Jean Michel pointed out in his pioneering paper in 1783, a black hole still exerts a gravitational force on nearby objects. Astronomers have observed a number of systems in which 2 stars orbit around each other, attracted toward each other by gravity. They also observe systems in which there is only one visible star that is orbiting around some unseen companion. One cannot, of course, immediately conclude that the companion is a black hole. It might merely be a star that is too faint to be seen. However, some of these systems, like the one called Cygnus X1, are also strong sources of X-rays. The best explanation for this phenomenon is that the X-rays are generated by matter that has been blown off the surface of the visible star. As it falls toward the unseen companion, it develops a spiral motion, rather like water running out of a bath, and it gets very hot, emitting X-rays. For this mechanism to work, the unseen object has to be very small, like a white dwarf, neutron star, or black hole. Now, from the observed motion of the visible star, one can determine the lowest possible mass of the unseen object. In the case of Cygnus X1, this is about 6 times the mass of the Sun. According to Chandrasekhar's result, this is too much for the unseen object to be a white dwarf. It is also too large a mass to be a neutron star. It seems, therefore, that it must be a black hole. There are other models to explain Cygnus X1 that do not include a black hole, but they are all rather far-fetched. A black hole seems to be the only really natural explanation of the observations. Despite this, I have a bet with Kip Thorne of the California Institute of Technology that in fact Cygnus X1 does not contain a black hole. This is a form of insurance policy for me. I've done a lot of work on black holes, and it would all be wasted if it turned out that black holes do not exist. But in that case, I would have the consolation of winning my bet, which would bring me 4 years of the magazine Private Eye. If black holes do exist, Kip will get only 1 year of Penthouse, because when we made the bet in 1975, we were 80% certain that Cygnus was a black hole. By now, I would say that we are about 95% certain, but the bet has yet to be settled. There is evidence for black holes in a number of other systems in our galaxy, and for much larger black holes at the centers of other galaxies and quasars. One can also consider the possibility that there might be black holes with masses much less than that of the Sun. Such black holes could not be formed by gravitational collapse, because their masses are below the Chandrasekhar mass limit. Stars of this low mass can support themselves against the force of gravity even when they have exhausted their nuclear fuel. So low-mass black holes could form only if matter were compressed to enormous densities by very large external pressures. Such conditions could occur in a very big hydrogen bomb. The physicist John Wheeler once calculated that if one took all the heavy water in all the oceans of the world, one could build a hydrogen bomb that would compress matter at the center so much that a black hole would be created. Unfortunately, however, there would be no one left to observe it. A more practical possibility is that such low-mass black holes might have been formed in the high temperatures and pressures of the very early universe. Black holes could have been formed if the early universe had not been perfectly smooth and uniform, because then a small region that was denser than average could be compressed in this way to form a black hole. But we know that there must have been some irregularities, because otherwise the matter in the universe would still be perfectly uniformly distributed at the present epoch, instead of being clumped together in stars and galaxies. Whether or not the irregularities required to account for stars and galaxies would have led to the formation of a significant number of these primordial black holes depends on the details of the conditions in the early universe. So, if we could determine how many primordial black holes there are now, we would learn a lot about the very early stages of the universe. Primordial black holes with masses of more than 1,000 million tons, the mass of a large mountain, could be detected only by their gravitational influence on other visible matter, or on the expansion of the universe. However, as we shall learn in the next lecture, black holes are not really black after all. They glow like a hot body, and the smaller they are, the more they glow. So, paradoxically, smaller black holes might actually turn out to be easier to detect than large ones. Fourth lecture. Black holes ain't so black. Before 1970, my research on general relativity had concentrated mainly on the question of whether there had been a Big Bang singularity. However, one evening in November of that year, shortly after the birth of my daughter, Lucy, I started to think about black holes as I was getting into bed. My disability made this rather a slow process, so I had plenty of time. At that date, there was no precise definition of which points in space-time lay inside a black hole and which lay outside. I had already discussed with Roger Penrose the idea of defining a black hole as the set of events from which it was not possible to escape to a large distance. This is now the generally accepted definition. It means that the boundary of the black hole, the event horizon, is formed by rays of light that just fail to get away from the black hole. Instead, they stay forever, hovering on the edge of the black hole. It is a bit like running away from the police and managing to keep one step ahead, but not being able to get clear away. Suddenly I realized that the paths of these light rays could not be approaching one another, because if they were, they must eventually run into each other. It would be like meeting someone else running away from the police in the opposite direction. You would both be caught, or, in this case, fall into a black hole. But if these rays of light were swallowed up by the black hole, then they could not have been on the boundary of the black hole. So light rays in the event horizon had always to be moving parallel to or away from each other. Another way of seeing this is that the event horizon, the boundary of the black hole, is like the edge of a shadow. It is the edge of the light of escape to a great distance, but equally it is the edge of the shadow of impending doom. And if you look at the shadow cast by a source at a great distance, such as the sun, you will see that the rays of light on the edge are not approaching each other. If the rays of light that form the event horizon, the boundary of the black hole, can never approach each other, the area of the event horizon could stay the same, or increase with time. It could never decrease, because that would mean that at least some of the rays of light in the boundary would have to be approaching each other. In fact, the area would increase whenever matter or radiation fell into the black hole. Also, suppose two black holes collided and merged together to form a single black hole. Then the area of the event horizon of the final black hole would be greater than the sum of the areas of the event horizons of the original black holes. This non-decreasing property of the event horizon's area placed an important restriction on the possible behavior of black holes. I was so excited with my discovery that I did not get much sleep that night. The next day I rang up Roger Penrose. He agreed with me. I think, in fact, that he had been aware of this property of the area. However, he had been using a slightly different definition of a black hole. He had not realized that the boundaries of the black hole, according to the two definitions, would be the same, provided the black hole had settled down to a stationary state. The second law of thermodynamics. The non-decreasing behavior of a black hole's area was very reminiscent of the behavior of a physical quantity called entropy, which measures the degree of disorder of a system. It is a matter of common experience that disorder will tend to increase if things are left to themselves. One has only to leave a house without repairs to see that. One can create order out of disorder. For example, one can paint the house. However, that requires expenditure of energy, and so decreases the amount of ordered energy available. A precise statement of this idea is known as the second law of thermodynamics. It states that the entropy of an isolated system never decreases with time. Moreover, when two systems are joined together, the entropy of the combined system is greater than the sum of the entropies of the individual systems. For example, consider a system of gas molecules in a box. The molecules can be thought of as little billiard balls, continually colliding with each other and bouncing off the walls of the box. Suppose that initially the molecules are all confined to the left-hand side of the box by a partition. If the partition is then removed, the molecules would tend to spread out and occupy both halves of the box. At some later time they could, by chance, all be in the right half, or all be back in the left half. However, it is overwhelmingly more probable that there will be roughly equal numbers in the two halves. Such a state is less ordered or more disordered than the original state in which all the molecules were in one half. One therefore says that the entropy of the gas has gone up. Similarly, suppose one starts with two boxes, one containing oxygen molecules and the other containing nitrogen molecules. If one joins the boxes together and removes the intervening wall, the oxygen and the nitrogen molecules will start to mix. At a later time, the most probable state will be to have a thoroughly uniform mixture of oxygen and nitrogen molecules throughout the two boxes. This state will be less ordered, and hence have more entropy than the initial state of two separate boxes. The second law of thermodynamics has a rather different status than that of the other laws of science. Other laws, such as Newton's law of gravity, for example, are absolute law. That is, they always hold. On the other hand, the second law is a statistical law. That is, it does not hold always, just in the vast majority of cases. The probability of all the gas molecules in our box being found in one half of the box at a later time is many millions of millions to one, but it could happen. However, if one has a black hole around, there seems to be a rather easier way of violating the second law. Just throw some matter with a lot of entropies, such as a box of gas, down the black hole. The total entropy of matter outside the black hole would go down. One could, of course, still say that the total entropy, including the entropy inside the black hole, has not gone down. But since there is no way to look inside the black hole, we cannot see how much entropy the matter inside it has. It would be nice, therefore, if there were some feature of the black hole by which observers outside the black hole could tell its entropy. This should increase whenever matter carrying entropy fell into the black hole. Following my discovery that the area of the event horizon increased whenever matter fell into a black hole, a research student at Princeton named Jacob Bekenstein suggested that the area of the event horizon was a measure of the entropy of the black hole. As matter carrying the entropy fell into the black hole, the area of the event horizon would go up, so that the sum of the entropy of matter outside the black holes and the area of the horizons would never go down. This suggestion seemed to prevent the second law of thermodynamics from being violated in most situations. However, there was one fatal flaw. If a black hole has entropy, then it ought also to have a temperature. But a body with a non-zero temperature must emit radiation at a certain rate. It is a matter of common experience that if one heats up a poker in the fire, it glows red-hot and emits radiation. However, bodies at lower temperatures emit radiation too. One just does not normally notice it, because the amount is fairly small. This radiation is required in order to prevent violations of the second law. So black holes ought to emit radiation, but by their very definition, black holes are objects that are not supposed to emit anything. It therefore seemed that the area of the event horizon of a black hole could not be regarded as its entropy. In fact, in 1972, I wrote a paper on this subject with Brandon Carter and an American colleague, Jim Bardeen. We pointed out that, although there were many similarities between entropy and the area of the event horizon, there was this apparently fatal difficulty. I must admit that in writing this paper, I was motivated partly by irritation with Bekenstein, because I felt he had misused my discovery of the increase of the area of the event horizon. However, it turned out in the end that he was basically correct, though in a manner he had certainly not expected. Black hole radiation. In September 1973, while I was visiting Moscow, I discussed black holes with two leading Soviet experts, Yakov Zeldovich and Alexander Starobinsky. They convinced me that, according to the quantum mechanical uncertainty principle, rotating black holes should create and emit particles. I believe their arguments on physical grounds, but I did not like the mathematical way in which they calculated the emission. I therefore set about devising a better mathematical treatment, which I described at an informal seminar in Oxford at the end of November 1973. At that time I had not done the calculations to find out how much would actually be emitted. I was expecting to discover just the radiation that Zeldovich and Starobinsky had predicted from rotating black holes. However, when I did the calculation, I found, to my surprise and annoyance, that even non-rotating black holes should apparently create and emit particles at a steady rate. At first I thought that this emission indicated that one of the approximations I had used was not valid. I was afraid if Bekenstein found out about it, he would use it as a further argument to support his idea about the entropy of black holes, which I still did not like. However, the more I thought about it, the more it seemed that the approximations really ought to hold. But what finally convinced me that the emission was real was that the spectrum of the emitted particles was exactly that which would be emitted by a hot body. The black hole was emitting particles at exactly the correct rate to prevent violations of the second law. Since then, the calculations have been repeated in a number of different forms by other people. They all confirm that a black hole ought to emit particles and radiation as if it were a hot body with a temperature that depends only on the black hole's mass. The higher the mass, the lower the temperature. One can understand this emission in the following way. What we think of as empty space cannot be completely empty, because that would mean that all the fields, such as the gravitational field and the electromagnetic field, would have to be exactly zero. However, the value of a field and its rate of change with time are like the position and velocity of a particle. The uncertainty principle implies that the more accurately one knows one of these quantities, the less accurately one can know the other. So, in an empty space, the field cannot be fixed at exactly zero, because then it would have both the precise value, 0, and a precise rate of change, also 0. Instead, there must be a certain minimum amount of uncertainty, or quantum fluctuations, in the value of a field. One can think of these fluctuations as pairs of particles of light or gravity that appear together at some time, move apart, and then come together again and annihilate each other. These particles are called virtual particles. Unlike real particles, they cannot be observed directly with a particle detector. However, their indirect effects, such as small changes in the energy of electron orbits and atoms, can be measured and agree with the theoretical predictions to a remarkable degree of accuracy. By conservation of energy, one of the partners in a virtual particle pair will have positive energy, and the other partner will have negative energy. The one with negative energy is condemned to be a short-lived virtual particle. This is because real particles always have positive energy in normal situations. It must therefore seek out its partner and annihilate it. However, the gravitational field inside a black hole is so strong that even a real particle can have negative energy there. It is therefore possible, if a black hole is present, for the virtual particle with negative energy to fall into the black hole and become a real particle. In this case, it no longer has to annihilate its partner. Its forsaken partner may fall into the black hole as well. But because it has positive energy, it is also possible for it to escape to infinity as a real particle. To an observer at a distance, it will appear to have been emitted from the black hole. The smaller the black hole, the less far the particle with negative energy will have to go before it becomes a real particle. Thus, the rate of emission will be greater, and the apparent temperature of the black hole will be higher. The positive energy of the outgoing radiation would be balanced by a flow of negative energy particles into the black hole. By Einstein's famous equation, E equals mc squared, energy is equivalent to mass. A flow of negative energy into the black hole therefore reduces its mass. As the black hole loses mass, the area of its event horizon gets smaller, but this decrease in the entropy of the black hole is more than compensated for by the entropy of the emitted radiation, so the second law is never violated. Black hole explosions. The lower the mass of the black hole, the higher its temperature is. So as the black hole loses mass, its temperature and rate of emission increase. It therefore loses mass more quickly. What happens when the mass of the black hole eventually becomes extremely small is not quite clear. The most reasonable guess is that it would disappear completely in a tremendous final burst of emission, equivalent to the explosion of millions of H-bombs. A black hole with a mass a few times that of the Sun would have a temperature of only 1/10,000,000th of a degree above absolute zero. This is much less than the temperature of the microwave radiation that fills the universe, about 2.7 degrees above absolute zero. So such black holes would give off less than they absorb, though even that would be very little. If the universe is destined to go on expanding forever, the temperature of the microwave radiation will eventually decrease to less than that of such a black hole. The hole will then absorb less than it emits and will begin to lose mass. But even then, its temperature is so low that it would take about 10 to the power of 66 years to evaporate completely. This is much longer than the age of the universe, which is only about 10 to the power of 10 years. On the other hand, as we learned in the last lecture, there might be primordial black holes with a very much smaller mass than were made by the collapse of irregularities in the very early stages of the universe. Such black holes would have a much higher temperature and would be emitting radiation at a much greater rate. A primordial black hole with an initial mass of 1,000 million tons would have a lifetime roughly equal to the age of the universe. Primordial black holes with initial masses less than this figure would already have completely evaporated. However, those with slightly greater masses would still be emitting radiation in the form of X-rays and gamma rays. These are like waves of light, but with a much shorter wavelength. Such holes hardly deserve the epithet black. They are really white hot and are emitting energy at the rate of about 10,000 megawatts. One such black hole could run 10 large power stations if only we could harness its output. This would be rather difficult, however. The black hole would have to be the mass of a mountain compressed into the size of the nucleus of an atom. If you had one of these black holes on the surface of the Earth, there would be no way to stop it falling through the floor to the center of the Earth. It would oscillate through the Earth and back until eventually it settled down at the center. So the only place to put such a black hole, in which one might use the energy that it emitted, would be in orbit around the Earth. And the only way that one could get it to orbit the Earth would be to attract it there by towing a large mass in front of it, rather like a carrot in front of a donkey. This does not sound like a very practical proposition, at least not in the immediate future. The search for primordial black holes. But even if we cannot harness the emissions from these primordial black holes, what are our chances of observing them? We could look for the gamma rays that the primordial black holes emit during most of their lifetime. Although the radiation from most would be very weak because they are far away, the total from all of them might be detectable. We do indeed observe such a background of gamma rays. However, this background was probably generated by processes other than primordial black holes. One can say that the observations of the gamma-ray background do not provide any positive evidence for primordial black holes. But they tell us that, on average, there cannot be more than 300 little black holes in every cubic light-year in the universe. This limit means that primordial black holes could make up at most 1/1,000,000th of the average mass density in the universe. With primordial black holes being so scarce, it might seem unlikely that there would be one that was near enough for us to observe on its own. But since gravity would draw primordial black holes toward any matter, they should be much more common in galaxies. If they were, say, 1,000,000 times more common in galaxies, then the nearest black hole to us would probably be at a distance of about 1,000 million kilometers, or about as far as Pluto, the farthest known planet. At this distance, it would still be very difficult to detect the steady emission of a black hole, even if it was 10,000 megawatts. In order to observe a primordial black hole, one would have to detect several gamma-ray quanta coming from the same direction within a reasonable space of time, such as a week. Otherwise, they might simply be part of the background. But Planck's quantum principle tells us that each gamma-ray quantum has a very high energy because gamma rays have a very high frequency. So to radiate even 10,000 megawatts would not take many quanta. And to observe these few quanta coming from the distance of Pluto would require a larger gamma-ray detector than any that have been constructed so far. Moreover, the detector would have to be in space, because gamma rays cannot penetrate the atmosphere. Of course, if a black hole as close as Pluto were to reach the end of its life and blow up, it would be easy to detect the final burst of emission. But if the black hole has been emitting for the last 10 or 20,000 million years, the chances of it reaching the end of its life within the next few years are really rather small. It might equally well be a few million years in the past or future. So in order to have a reasonable chance of seeing an explosion before your research grant runs out, one would have to find a way to detect any explosions within a distance of about 1 light-year. One would still have the problem of needing a large gamma-ray detector to observe several gamma-ray quanta from the explosion. However, in this case, it would not be necessary to determine that all the quanta came from the same direction. It would be enough to observe that they all arrived within a very short time interval to be reasonably confident that they were coming from the same burst. One gamma-ray detector that might be capable of spotting primordial black holes is the entire Earth's atmosphere. We are, in any case, unlikely to be able to build a larger detector. When a high-energy gamma-ray quantum hits the atoms in our atmosphere, it creates pairs of electrons and positrons. When these hit other atoms, they in turn create more pairs of electrons and positrons. So one gets what is called an electron shower. The result is a form of light called Cherenkov radiation. One can therefore detect gamma-ray bursts by looking for flashes of light in the night sky. Of course, there are a number of other phenomena, such as lightning, which can also give flashes in the sky. However, one could distinguish gamma-ray bursts from such effects by observing flashes simultaneously at 2 or more fairly widely separated locations. A search like this has been carried out by 2 scientists from Dublin, Neil Porter and Trevor Weeks, using telescopes in Arizona. They found a number of flashes, but none that could be definitely ascribed to gamma-ray bursts from primordial black holes. Even if the search for primordial black holes proves negative, as it seems it may, it will still give us important information about the very early stages of the universe. If the early universe had been chaotic or irregular, or if the pressure of matter had been low, one would have expected it to produce many more primordial black holes than the limit set by our observations of the gamma-ray background. It is only if the early universe were very smooth and uniform, and with a high pressure, that one can explain the absence of observable numbers of primordial black holes. General relativity and quantum mechanics. Radiation from black holes was the first example of a prediction that depended on both of the great theories of this century, general relativity and quantum mechanics. It aroused a lot of opposition initially because it upset the existing viewpoint. How can a black hole emit anything? When I first announced the result of my calculations at a conference at the Rutherford Laboratory near Oxford, I was greeted with general incredulity. At the end of my talk, the chairman of the session, John G. Taylor from King's College London, claimed it was all nonsense. He even wrote a paper to that effect. However, in the end, most people, including John Taylor, have come to the conclusion that black holes must radiate like hot bodies if our other ideas about general relativity and quantum mechanics are correct. Thus, even though we have not yet managed to find a primordial black hole, there is fairly general agreement that if we did, it would have to be emitting a lot of gamma and X-rays. If we do find one, I will get the Nobel Prize. The existence of radiation from black holes seems to imply that gravitational collapse is not as final and irreversible as we once thought. If an astronaut falls into a black hole, its mass will increase. Eventually, the energy equivalent of that extra mass will be returned to the universe in the form of radiation. Thus, in a sense, the astronaut will be recycled. It would be a poor sort of immortality, however, because any personal concept of time for the astronaut would almost certainly come to an end as he was crushed out of existence inside the black hole. Even the types of particle that were eventually emitted by the black hole would in general be different from those that made up the astronaut. The only feature of the astronaut that would survive would be his mass or energy. The approximations I used to derive the emission from black holes should work well when the black hole has a mass greater than a fraction of a gram. However, they will break down at the end of the black hole's life, when its mass gets very small. The most likely outcome seems to be that the black hole would just disappear, at least from our region of the universe. It would take with it the astronaut and any singularity there might be inside the black hole. This was the first indication that quantum mechanics might remove the singularities that were predicted by classical general relativity. However, the methods that I and other people were using in 1974 to study the quantum effects of gravity were not able to answer questions such as whether singularities would occur in quantum gravity. From 1975 onward, I therefore started to develop a more powerful approach to quantum gravity based on Feynman's idea of a sum over histories. The answers that this approach suggests for the origin and fate of the universe will be described in the next 2 lectures. We shall see that quantum mechanics allows the universe to have a beginning that is not a singularity. This means that the laws of physics need not break down at the origin of the universe. The state of the universe and its contents, like ourselves, are completely determined by the laws of physics, up to the limit set by the uncertainty principle. So much for free will. 5th lecture. The Origin and Fate of the Universe. Throughout the 1970s, I had been working mainly on black holes. However, in 1981, my interest in questions about the origin of the universe was reawakened when I attended a conference on cosmology in the Vatican. The Catholic Church had made a bad mistake with Galileo when it tried to lay down the law on a question of science, declaring that the sun went around the earth. Now, centuries later, it had decided it would be better to invite a number of experts to advise it on cosmology. At the end of the conference, the participants were granted an audience with the Pope. He told us that it was okay to study the evolution of the universe after the Big Bang, but we should not inquire into the Big Bang itself, because that was the moment of creation, and therefore the work of God. I was glad then that he did not know the subject of the talk I had just given at the conference. I had no desire to share the fate of Galileo. I have a lot of sympathy with Galileo, partly because I was born exactly 300 years after his death. The hot Big Bang model. In order to explain what my paper was about, I shall first describe the generally accepted history of the universe, according to what is known as the hot Big Bang model. This assumes that the universe is described by a Friedmann model, right back to the Big Bang. In such models, one finds that as the universe expands, the temperature of the matter and radiation in it will go down. Since temperature is simply a measure of the average energy of the particles, this cooling of the universe will have a major effect on the matter in it. At very high temperatures, particles will be moving around so fast that they can escape any attraction toward each other, caused by the nuclear or electromagnetic forces. But as they cooled off, one would expect particles that attract each other to start to clump together. At the Big Bang itself, the universe had zero size, and so must have been infinitely hot. But as the universe expanded, the temperature of the radiation would have decreased. 1 second after the Big Bang, it would have fallen to about 10,000 million degrees. This is about 1,000 times the temperature at the center of the Sun, but temperatures as high as this are reached in H-bomb explosions. At this time, the universe would have contained mostly photons, electrons, and neutrinos, and their antiparticles, together with some protons and neutrons. As the universe continued to expand and the temperature to drop, the rate at which electrons